This corollary, now we have taken a specific value of n, although this may look like a very large, and indeed it is going to be very large. Yes, it is going to be very large value of n, then n times n plus 1 is even. And why is this a corollary to this theorem? Because here n can be any integer, so this particular case is a corollary. Okay, in this case also we know that n times n plus 1 is an even integer. Right. Now, suppose you don't have vacuous truth and you want to prove this corollary. Okay. So what you do first of all, you check the parity of n, or you go through the proof like that. For example, how we went through the proof in the actual proof of the theorem when n is even or we don't know. See, at this point we still don't know what n is, but we can quickly determine what n is. You see, we can we are not going to find the actual value of n. That would be a daunting task, but we want to find whether n is even or odd. That is not very difficult. You see, this is an odd integer, the first one. The second one is also odd. Why? Because the last digits are not divisible by 2. So sum of two odd integers is even. And you are multiplying an even integer with itself. How many times? 20,419 times. How many times? It does not matter. When you multiply two even integers or any number of even integers, the result is an even integer. So this whole power is an even integer. Now look at this term. 241 is an odd integer. And just like product of even integers is even, a product of a number of odd integers is odd. Okay, so this and introducing a minus sign does not change the fact that it is odd. So this is odd. Add 1 to that and this becomes even. Now we have even integer plus even integer. So that gives us even integer. So then you can carry out the proof. Okay, now you know for sure that n is even. So you can carry out one or the other part of the part of the proof where n is even. Do you see the difference? Now you cannot just simply write both you don't need to write both the parts of the proof. You can write only that part where n is even. Now you know for sure that n is even. But do you see the extra work that we have to do here? And why bother for that? Instead, we can just introduce, or like we have done, in the implication we can simply assume the implication to be true when x is false, regardless of the state of y. And that allows us to write more neat proofs. Okay, so that's why this convention. It's a very convenient convention and we keep using it. Vacuous truths are useful in this way. Okay, so that is the reason we went through this theorem and the proof. That's the main reason. We are calling it a theorem, but it's not really a theorem. You may have come across these terms: lemma, proposition, then theorem, corollary. You may have come across these terms. All of them are mathematical results. Okay, all of them are mathematical statements that are true. Lemma, now but the use of different types of names suggests that there is something happening. I mean, there is something, how can I say it? It represents how important a given result is. A lemma is a minor result which can be proved relatively easily using the hypothesis and some elementary properties of the objects involved, of the mathematical objects involved. So it's rather easy to derive result. It's not that important but somewhat necessary. Propositions are also results which can be obtained with somewhat more effort than a lemma, and you can use a lemma to prove a proposition. So lemma is the first stage. Like for example, in a very complicated proof where you have many different parts, you can, instead of carrying out the proof from start to finish in a single proof, you can divide it up into a number of results and then use those results to finish the proof. So the most elementary parts of that proof will be lemmas, and then using lemmas you can